Okay, so we're going to finish with lesson 18, which we were working on Friday before spring break. And let me know if you have any questions about this lesson at all while we are out for the week following spring break because of coronavirus precautions. So what we did on the Friday before spring break was we solved for the generic equation for a weak base and its equilibrium expression, and I told y'all to go ahead and work on problem 7. And so we're going to pick up right there. We're told to calculate the pH of a certain molar solution of methylamine. Its formula is right here, and we're told that the Kb is this following value. So even if we weren't sure if it was a base, we know it's a base because of the Kb, and we know that it's a weak base also because of the Kb, and because it's not one of our strong bases we talked about at the beginning of lesson 18. So we're going to set up our ice table, because anytime we see a weak base or acid, we should think ice table. I'm going to go ahead and just use my generic weak base expression for my ice table because methylamine, its formula is a lot to write out. So I'm just going to use base to describe methylamine and then the Hb plus for its conjugate acid and hydroxide. Remember, water is not going to show up in our expression. I'm going to go ahead and plug in my initial amounts, which is 0.85 molar of the weak base, none of my conjugate acid, none of my hydroxide, which has been something we've seen in several problems thus far. This tells me that equilibrium is going to shift to the right to produce products and consume reactants. So I'm going to use minuses and pluses with the x variables to show that change. And then I plus C equals E. Same thing we've been doing since we started equilibrium. Now I have my Kb values I can plug in, but we learned about a rule last time that if our Kb multiplied by 1,000 is less than the starting amount, initial concentration that we're given, that we can ignore the minus x that's in that equilibrium row. So I'm going to take my Kb, multiply it by 1,000, and I get this value, and I see that it's much smaller than 0.85, which means I can go ahead and remove the minus x. But the x plus and the x plus on the right hand side have to stay there because I need to know what x is equal to. I just don't have to worry about what minus x is equal to because it's so small compared to what I'm starting with that it's essentially negligible. So now I'm going to plug in my Kb values. I'm going to do my products over my reactants. Same thing we've been doing since the beginning, products divided by reactants. I get to leave off that minus x. And I'm going to set that all equal to my Kb value. After I do rearrangement, multiply the 0.85 onto both sides, then take the square root because of the x squared. I'm going to get that x is equal to 0.0193 molar. Okay. And the problem tells me to solve for the pH, which I have the hydroxide concentration because I know what x is equal to. And so if I plug that into a formula we learned in lesson 17, which is that the negative log of the hydroxide concentration will give me POH, that gets me a little bit closer to answering the problem. And that's that the POH is equal to 1.71. Which doesn't answer the problem of pH, but if you remember we learned about another formula in lesson 17, which is that the pH plus POH is equal to 14. I can plug in the POH I just solved for and subtract that from 14 to get that the pH is equal to 12.29. Which makes total sense because this is a weak base. Basic solutions, we should expect the pH to be between 7 and 14, and it's 12.29, which agrees with our hypothesis about expected pH. Now you're going to see here that 18.C is omitted, and I want you to ignore it. It's not going to be, we're just not going to concern ourselves with dilute solutions at this point. Okay? So percent ionization is the last part of this lesson, and I want you to think of the percent ionization formula. which is the amount ionized at equilibrium divided by initial concentration. It's very similar to mole fraction. The moles of A divided by the total moles gives us how many moles are responsible to A out of the total, and that's kind of what this is looking at as well. Now the problem that we're told is to calculate the percent ionization of 0.08 molar of hydrofluoric acid. This is a weak acid, so I'm going to think of ICE table immediately, and I'm given an HF value of 7.1 times 10 to the negative fourth. So I'm going to write out my expression. And I know it seems redundant to keep writing water and to keep writing these expressions each and every time, but I'm going to tell you it's very helpful if you can get quick at these and you are confident in setting them up, because we're just not done with equilibrium quite yet. We've got a few more lessons and a whole nother chapter on equilibrium before we are done. So my ICE table, my equilibrium is going to shift to the right hand side to produce products, consume reactants. I write in my equilibrium row, which is what I need for my Ka expression. Now I get to test my rule about ignoring that minus x. So I take the Ka and multiply it by 1,000 and get 0.71, which I see is much greater than my initial concentration, which means I cannot ignore this. I have to keep the minus x in my expression because it is significant at this point. So I'm going to take products divided by reactants, keeping the minus x in my expression. And what this is going to lead to is a quadratic. So I'm going to start kind of unpacking the problem, if you will. Distributing the, sorry, let me do that the other way. I don't like putting negatives in front of numbers like that. Take the Ka and multiply it by the initial concentration, and take the Ka and multiply it by the minus x. Now I need to move everything either to the left or the right. I'm of the mindset I like fewer negative numbers, so I'm going to move everything to the left-hand side so that I have a positive plus x, a positive plus x squared, a positive x squared, and only one negative value. So my A is going to be equal to 1, my B is equal to my Ka, and my C is equal to my Ka times my initial concentration. Okay? So if you had moved everything to the right-hand side, A would be negative, B would be negative, and C would be positive. So all the signs are just opposite, but it doesn't make any difference in your final result. So now, unless you make a mistake, now that my answers are in the terms of A, B, and C, I'm going to plug them into the quadratic. I usually take these problems step by step because I don't like to make a mistake on these problems. You don't always see that you've made a mistake. So I recommend solving for each piece one at a time. Like, for example, multiply out the 4 times 1 times, well, maybe you don't have to multiply by 1, but 4 times 1 times the C, and then square the Ka value, and then subtract them, and then take the square root. Just do it step by step so you don't make a mistake. Okay? If you can get fast enough at your ICE tables, you should have plenty of time to solve for this and do it correctly. So once we solve for everything under the square root, we should get 0.01509. And now we have two options. I'm either going to subtract or add the two values together. And that will be my x value, and only one of them can be right. So what you can see here is if we have two negative numbers, we add them together, it becomes even more negative, which means that this cannot be, oh, I don't want to make that this cannot be possible. Okay, we cannot have a negative x, meaning that only adding them together is correct, and my final answer comes out to be 0.00719 molar, and that's what x is equal to. So that's this value, and then that value. Now, with the percent ionization, the number of ions formed is x, so that's also going to be my numerator. My initial or starting amount is what I was given in the problem, which is 0.08 molar, and then multiply it by 100%. And the value you should get is 8.99%, which what this tells me is that 8.99% of all the hydrofluoric acid in solution dissociates into fluoride and hydronium ions, whereas the other 91.01% stays together as hydrofluoric acid and does not dissociate into solution. Okay, so we can see that it's incomplete ionization, which we would expect because it's a weak acid, and we said that they do not fully dissociate into solution 100%. It's going to be less than 100%. So at this point, you're going to need to go on and listen to lesson 19. Please make sure you also take the quiz and do all the things that are assigned as part of today's class that we are doing online because of the coronavirus.